Hello and welcome back. Today we'll be doing question 3 from the 2003 Step Paper 2. We'll also be doing an extension question since the solution to the original step question is actually rather simple. So, let's get started. Question 3. Prove that the cube root of any irrational number is itself an irrational number. Let un be 5 to the 1 over 3 to the n. Given that the cube root of 5 is an irrational number, prove by induction that un is an irrational number for every positive integer n. Hence, or otherwise, give an example of an infinite sequence of irrational numbers which converges to a given integer m. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started with part 1. Here, we'll firstly let the cube root of a number n be rational, that is in the form p over q, where p and q are integers. We'll also say that n is irrational. However, this implies that n is equal to p cubed over q cubed, and since p cubed and q cubed are both integers, this implies that n is in fact rational, a contradiction, and thus the cube root of any irrational number remains irrational, as required. We'll now move on to the second statement of the original question. Here we have the number un plus 1, and this is equal to 5 to the 1 over 3 to the n plus 1. This is equal to the cube root of 5 to the 1 over 3 to the n, and this is therefore equal to un to the 1/3. But since u1 is irrational, by induction we have that un is irrational for all n is a positive integer, as required. Now we'll move on to the final part of the question. Here we'll notice that un converges to 1 as n tends towards infinity, and therefore an example of the required sequence would be an is equal to m plus un take away 1. As un converges towards 1, the sequence an will converge towards m as required. Now we'll move on to the extension question which I've written. Define the sequence an by an is equal to m plus -1 all to the n multiplied by phi to the n, take away the floor of phi to the n, all over the square root of fn, where fn is equal to phi to the n take psi to the n, all over root 5, which is the nth Fibonacci number. Phi is the golden ratio, and psi is 1 minus phi, which is the conjugate of phi. Prove that an is rational if and only if phi to the n take floor of phi to the n is a rational multiple of the square root of fn. Show further that this only occurs when n is equal to 3k, where k is a positive integer. Pause the video again and have a think, and once you're ready, restart to see if you were correct. Let's continue with this part of the question. We'll firstly prove this in the reverse direction. If phi to the n take the floor of phi to the n is a rational multiple of the square root of fn, then phi to the n take floor phi to the n all over the square root of fn is rational, meaning that an is rational since m is already a rational number. Similarly, if an is to be rational, since m is definitely rational, we must have that the fraction is rational, meaning that the numerator must be a rational multiple of our denominator. Thus, an is rational if and only if phi to the n take floor phi to the n is a rational multiple of the square root of fn, as required. Now we'll prove that this is only possible when n is a multiple of 3. Using phi to the n is equal to fn phi plus fn minus 1, we have that phi to the n take floor phi to the n is equal to fn phi take floor of fn phi, and this is equal to q of the square root of fn. Fn phi take q of the square root of fn is therefore equal to the floor of fn phi, which is an integer. Setting the square root of fn to be s, we therefore have phi s squared take qs is an integer, and therefore we have phi s squared take qs is equal to k, where k is an integer. Substituting fn back for s squared, we have fn phi take qs equals k, which is an integer. And this is only possible when q is equal to 0 or n is equal to 3k. We'll look at q equals 0 first. This is impossible, however, since phi to the n take floor phi to the n is never equal to 0. Now we'll look at the case where n is equal to 3k. Firstly, we'll notice that f of 3k is even for any k, and phi to the 3k is equal to f3k phi plus f3k minus 1. Using periodicity, the fractional part phi to the 3k take floor phi to the 3k aligns with the square root of f3k, all multiplied by psi to the 3k. By the identity psi to the 3k is equal to negative 1 all to the 3k, multiplied by phi to the negative 3k, the psi to the 3k term introduces a constant when n is equal to 3k, satisfying phi to the n take floor phi to the n is equal to q multiplied by the square root of fn. Thus, we have proven that an is rational only when n is a multiple of 3. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.